on 1.7 periodic trends of AP Chemistry's Unit 1. This one's going to be a really long one, guys. Not because the content's particularly difficult, it's because every answer is going to require you to give a very thorough explanation of why this trend exists. So that is the part that you really need to practice, in addition to knowing the definitions of each of these periodic trends very well. Okay, so the relationship between this and atomic structure and Coulomb's law are huge part of AP chemistry. It's very typical questions to see on free response questions. Okay, so first of all, I want to remind you the periodic table is organized based on patterns of recurring properties, right, of your different elements. So these relate to the ground state electron configurations, the subshells and orbitals that we reviewed. Now, you'll see the word periodicity. That's just a fancy term for the trends we've seen on the periodic table. So just know that's what we're referring to, the periodicity, the repeating trends. All right, 4 trends we got to know. Ionization energy. I've given you some abbreviations here as well to save a bit on writing because this is a lengthy one, guys. 2, we got atomic and ionic radii, right, which is radius plural for radius. Electron affinity and electronegativity. So you want to know that ionization energy, electron affinity, and electronegativity all increase in value up a group and toward the right. So we increase as we move up and increase toward the right across the periodic table. Atomic radius goes the opposite way. Okay, so the other 3, up and right, atomic radius is going to increase to the left and increase down, opposite trend. Now, what's the difference between atomic radius and ionic radius? Atomic radius refers to a neutral atom, right? The ionic radius refers specifically to the ion form, like a charged atom, right? So normally when we're dealing with ionic radius, it's going to be some sort of comparison, right, between 2 ions, 2 different charged ions, or an ion in its neutral version of that atom. So typically we're looking at a comparison with those, where atomic radius, we're looking for more of an explanation. All right, so definitions of each of these 4 trends. This we've just got to know. All right, ionization energy is the energy required to remove the most loosely held valence electron from an atom, the easiest to remove. Okay, so that's your ionization energy. Electron affinity, okay, is the energy released when a neutral atom in the gas state, that's what makes this one different. It's the only one where state matters. It gains an electron to form an anion. Okay, so this one's really specific. So it's about energy, right? This one's about just general energy. Right? Electronegativity is a tendency, not an energy. This is different. Tendency of an atom to attract electrons to form a bond. Okay, so this one's about bonding and attraction of electrons. Ionization energy is about removing electrons and how hard that is to do, how much energy it takes. Electron affinity is about the energy change overall, okay, when we form an anion. Radius is simply what you think it is. Radius is the size, right? And we define that as the distance from the nucleus to the valence shell. Right? You may find some more formal definitions about half the distance between the neighboring nuclei of identical atoms. It's just a more specific way in which we can measure these things. Now, ionic radius, right? Same thing, but it's just for ions, like we stated before, rather than the neutral atoms. Okay. So radius is distance. Okay. Electronegativity is about attracting electrons. To sum this up for you, electron affinity, right, is about energy release. Or I should say energy change. Let's call it energy change. That's more appropriate. Ionization energy, right, is about removing electrons. Okay, so we got attracting, removing, we've got distance, and then we've got an energy change. Okay, so you've got to be able to explain all 4 of these trends in terms of Coulomb's law, effective nuclear charge, and something called shielding. Shielding is less commonly discussed in AP than it once was. Shielding deals with those inner electrons, and how, when I discussed, if you watched my earlier videos, how they act almost as barriers, right, to that force that's trying to move past them, right? They're like obstacles for that force to get through as it's trying to penetrate further and further out into the valence shells, the outer shells. So it's a term we use. It's not common, so you don't necessarily have to state that term exactly. We're just describing what's happening. Nuclear charge and Coulomb's law all day long. You've got to be able to give good, thorough answers to those. And these are going to be some of the longest explanations that you provide all year, or the explanations due to Coulomb's law. Typically, your free response answers are very short. These require more words than the others often do. All right, so two that really, really matter is going to be the radius and the ionization energy. Those are going to be the two trends that you really have to put the most weight into explaining. Okay. So first things first, first example with radius. Does lithium or beryllium have a smaller radius? Justify in terms of Coulomb's law and atomic structure. Well, we can look at the trend since we're dealing with radius. We know it increases left and it increases down. Lithium and beryllium are right next to each other. So based on the trend, we know that lithium should be a larger atom as compared to beryllium. Okay, so it should have a larger radius. Beryllium should have a smaller radius. Okay, so let's see if we can explain this. Because they're both side by side, they're both in the second energy level, right? So their valence electrons are located in the second energy level, same period. Which means the distance part of Coulomb's law isn't very applicable here, right? So let's look at charge. And in order to really examine charge, we've got to look at the number of protons. So beryllium has 4 protons, lithium has 3. 4 is bigger than 3. Therefore, beryllium is going to have a greater nuclear charge. Right? And according to Coulomb's law, the greater the charge, the stronger the attractive force, right, between that nucleus and the valence electrons. Therefore, beryllium is going to experience a stronger attraction, force of attraction between the nucleus and the valence electrons, causing its radius to be smaller. That's the complete and thorough answer. Example 2, which of these has a smaller radius, lithium or sodium? Again, we're going to justify in terms of atomic structure and Coulomb's law. So this example, we're looking at lithium and sodium. Okay, our rules state, all right, we're looking at radius according to Coulomb's law. Radius increases left and down. Lithium is here, sodium is just beneath it. So this time we're in different energy levels. We are not side by side in the same energy level. Lithium is actually in the second, sodium's located in the third. So that means that lithium's valence electrons are in the second energy level, whereas sodium's are in the third energy level. Okay, so which one of these would be smaller? Well, according to the trend, we know that lithium should be smaller, sodium should be larger, but you can't give me that for an answer, right? That doesn't explain in terms of Coulomb's law. It just gives me an answer according to a pattern that you see. AP will not give you credit for that. Give me more detail, okay? Why? Well, lithium's atomic radius is going to be smaller because its valence electrons are closer to the nucleus. This one's about distance, right? Not charge, because we're at different energy levels. So according to Coulomb's law, the smaller the distance, the greater the force, right? So because lithium has a stronger attraction between the nucleus and its valence electrons, because they're in the second energy level, which is closer to the nucleus, a lesser distance, its radius is going to be smaller than that of sodium, which has valence electrons in the third energy level, which experiences a weaker force of attraction between the nucleus and its valence electrons. We're told to rank lithium, beryllium, and sodium in order of increasing atomic radius. Increasing means smallest to largest. That's something we need to know as well and get familiar with. Smallest to largest. So based on the information from our previous problems, 1 and 2, we could kind of compare those and see who we would expect to have, right? The smallest and the largest radius. So beryllium should be our smallest here, lithium in the middle, sodium would have our largest radius. All right, moving on to example 4. Who has the larger radius here, sodium or sodium plus 1? And you're told to justify this in terms of atomic structure. The first thing I want you to know is we're dealing with a neutral atom. Sodium with a plus 1 is an ion. So this is a neutral atom. This is an ion, which means that would be atomic radius, right? Right here, this is ionic radius. So this is an ionic radius question. And this is a comparison as we looked at before. You're told to justify your answer in terms of atomic structure. Okay, so the first thing I want to do when we're dealing with an ion, always go back to your electron configuration. Electron configurations, right, give us so much information on our valence electrons and how they are removed to form an ion. So first of all, sodium's electron configuration, 1s2, 2s2, 2p6, 3s1. This information was not given. You're expected to be able to do this based on previous lessons. Sodium with a +1, okay, 1s2, 2s2, 2p6. Because it has a +1 charge, that indicates that one electron has been removed, right, from the valence shell of sodium, of neutral sodium. Therefore, the 3s1 was removed, right? 3s1 removed from here to give us 1s2, 2s2, 2p6. Now, based on these two, I can tell you that sodium is going to have a larger radius than sodium plus. Why? You think this has to do with charge? Or does this have to do with distance? Let's think about this. Sodium and sodium plus, it doesn't matter, they're both sodium. They have the same number of protons. So both have how many protons? We referenced the periodic table, and that is 11. So they both have 11 protons. So charge isn't our biggest, right, answer here. What's going to make a difference for us is the distance, right? So notice that the valence electrons of sodium plus are in the 2p subshell, whereas the valence electrons of neutral sodium are in the 3s subshell. So therefore, sodium has a larger radius than sodium plus because Na's valence electron is in the third energy level, while sodium plus's valence electrons are in the second energy level. So this one is a distance thing again, right? So we're comparing the second energy level to the third, right? We know that Coulomb's law says, right, the closer electrons are to the nucleus, right, the lesser the distance, the greater the attractive force. Okay, therefore sodium plus should experience a greater attractive force, making its radius smaller as compared to neutral sodium's, which has valence electrons in the 3s, right, a further out. It should be a greater distance. Greater distance equals weaker force of attraction, therefore making it larger. So Na is larger. Example 5. Explain why the radius of Fe2 plus is larger than Fe3 plus in terms of atomic structure. Okay, so this time we have Fe2 plus and Fe3 plus. Both are ions. We're comparing the radii of two different ions. Again, when we're dealing with ions, our first point of reference needs to be going back to electron configuration. That should be your first step. Okay, so step 1, write the electron configurations. From there, we can see where those valence electrons are located. Then we can make some determinations. Okay, both versions of iron still have the same number of protons. Iron has 26 protons no matter what version of ion you get. Okay, so what is the difference, right? If we know we have the same protons, we should have, right, similar charge at this point. Okay, so what do we compare next? Well, okay, according to these electron configurations, Fe2 plus has 3d6, whereas Fe3 plus ends in 3d5. Same energy level, same number of protons. This one feels really tricky. It seems like the charge should be the same. It seems like the distance should be the same, but it's not, right? In truth, there are some differences. So although they have the same number of protons, because Fe3 plus has one less valence electron, right, the 3d5 versus 3d6, then its effective nuclear charge is greater. Why? Even though it has the same number of protons, that force is exerted out on a fewer number of electrons, right? So that allows that force to be a bit stronger as compared to it having to be split up or exerted out over a greater number of electrons. So in turn, what does that mean? It means its nuclear charge is more effective, right? Okay. So it has a more effective nuclear charge. So then we have a stronger attractive force, right, between the fewer electrons and the nucleus. That makes the Fe3 plus ion smaller in radius. Okay? Example 6, similar, but what if we have neutral F and F negative 1? Which one of these is going to be larger? Justify. Okay, when we're dealing with an ion, what's our rule? Always start with the electron configuration. So F is 1s2, 2s2, 2p5. F negative, therefore, must be 1s2, 2s2, 2p. What's a negative 1 charge? So we have gained 1 electron. So it is now 2p6. Right? Okay, so this is a similar situation to what we saw before, right? Except this time we're comparing a neutral atom to an ion. Now, which one of these two is larger? Okay, well, F negative has more valence electrons, one more specifically, has one more valence electron. Remember, F and F negative have the same number of protons, the same number of energy levels here, right? Their valence electrons are both in the 2p subshell. So we have to make that specific differentiation here based on the number of electrons, right? So because F negative has one more valence electron, that makes the attractive force between, right? Making the attractive force, made a mistake here, guys. Sorry about that. Let's fix that. Making the attractive force between the electrons and the nucleus weaker, therefore making the radius larger. Okay, so remember, more electrons over the same number of protons equals weaker force. That may term it in a way that's easier for you to remember. Weaker force. Okay, the weaker the force, the larger the radius. The stronger the force, right? And the smaller the radius. Okay, here you're given a series of ions, and you're told that these ions are isoelectronic, which means they have the same number of electrons, right? So that's a good term to know. Isoelectronic means same number of electrons. And you're told to arrange these ions in order of decreasing ionic radius and justify your answer. So here's what we know. They all have the same number of electrons. Same. Therefore, the atom with the most protons, right, compared to electrons, is going to have the greatest nuclear charge. And if we have a greater nuclear charge, according to Coulomb's law, right, it's going to have the greatest force of attraction to the valence electrons, making the radius smaller. So what we need to do is look at how many protons each of these ions has, because these are different. That's what makes this example different than the previous ones. The others, we were looking at different versions of an ion versus its neutral counterparts. They were the same. So we were looking at chlorine and chlorine -1, or chlorine -2, for example, different types of ions. Here we're looking at completely different elements, right? Ions of completely different elements. So we don't have inherently the same number of protons. So we've got to compare protons to electrons. So when I look at sodium, I see from the periodic table, sodium has 16 protons. This information was not given. I pulled this from the periodic table, which is what you would need to do in working this problem. Chlorine has 17, potassium's 19, calcium has 20. So the one with the most protons, right, is going to have the greatest nuclear charge, therefore the greatest force of attraction, therefore making the radius smaller. So calcium is going to be our smallest, right? Then potassium, then chlorine, and our largest here would be sulfur. Now this asks for decreasing, right, which means largest to smallest. So we really have to watch those terms, right? Largest to smallest, before you are asked to go in order of increasing. You really have to think about those, okay? All right, so the largest ionic radius, smallest ionic radius. All right, so that concludes the section on atomic and ionic radius. Now we're going to move on to ionization energy, right? The next trend that's really important for you guys to be able to give explanations for. So I want to remind you, ionization energy is the energy required to remove the most loosely held valence electron. Now, every time an electron is removed, you have another ionization energy value. So each electron has its own ionization energy value. So you can have a first ionization energy for the first electron, a second, if we were to remove a second one from the same atom, a third, a fourth, all the way up to 20th, however many are there, it can continue as far as it needs to go. Now, just as we did with radius, okay, we're going to have to use those same principles of atomic structure to explain, right, the ionization energy trend. So let's look at example 8. You're given a table of ionization energy values for electrons in magnesium. Now, given this table, you're told to explain why the ionization energy values increase as successive electrons are removed from the atom. So notice this one just keeps going up. It's bigger and then bigger, bigger, and this one's even bigger, and this one's even bigger. Right? So notice they just continue to increase. Now, as each electron is removed, right, the atom's charge increases in magnitude. How does that work? Let's think about this. After I remove the first one, I now have a magnesium plus 1 atom. After I remove the second one, I now have a magnesium plus 2 ion. After I remove the third, I have a magnesium plus 3 ion, so on and so forth. Okay, so that's what I'm referring to. Notice the magnitude of the charge of the ion increases every time I remove an electron. Well, according to Coulomb's law, right, the greater the magnitude of charge, the greater the attractive force between the nucleus and electrons, which means more energy is going to be required to remove the electron. Okay, let's go to part B of example 8. Why would you expect the second ionization energy for sodium to be higher than that of magnesium? Okay, so let's take a look. So if we weren't given any values, we don't have a lot of information. Why? Why would we expect those to be different? On the periodic table, sodium is located right next door to magnesium, side by side. They're in the same energy level. They're both in the third energy level. Just for reference, okay? And sodium has 11 protons, magnesium has 12. All right, so given what we know, let's have a look here. Since we're looking at ionization energy, which is dealing with the forming of ions, right? Hence ionization energy. Let's go back to what we did before. Let's have a look at those electron configurations. So for sodium, we've got 1s2, 2s2, 2p6, and 3s1. Magnesium, same, except for we end in 3s2. So if we were to remove a second electron from sodium, what would that look like? Well, removing one would take away the 3s shell. If I remove a second one, because we want to talk about the second ionization energy because the question said so, then that would leave me with 2p5. If I were to remove 2 electrons from magnesium, I would just get rid of the 3s subshell. So the second energy level is closer to the nucleus than the third, right? So removing an electron from the 2p subshell is going to require more energy, right, than removing an electron from the 3s subshell. So remember, according to Coulomb's law, the smaller the distance between the nucleus and the valence electrons, the stronger the force, right? Hence the second subshell, right, is closer to the nucleus than the third. Therefore, removing an electron from the second one would require more energy, right? And that would be for sodium, where we had to remove an electron from the second energy level from the 2p6 subshell. So that would mean that it's going to require more energy to remove a second electron from sodium than it does from magnesium in this case. Let's talk about some odd exceptions to this trend. There are a couple that exist. So if these were to pop up, I don't want these to be intimidating. So first, let's look at nitrogen as compared to oxygen. So based on the periodic table, nitrogen comes before oxygen. We say the ionization energy trends increase up and right. And we should have nitrogen and then oxygen. So in theory, oxygen's ionization energy should be higher, right? But it's not. In reality, oxygen's is 1314, whereas nitrogen's is 1402. Why is that? Let's have a look again, right? Like we did before at those electron configurations. Again, those aren't given. That's something that I expect you to be able to write on your own. So nitrogen ends in 2p3, oxygen ends in 2p4. So this is a little different. So what I want you to know is that oxygen has more electron-electron repulsions in 2p4 than nitrogen experiences in 2p3, which means that oxygen, because it has more repulsions, That makes it require a little less energy to remove in that P than it does in the P3 in nitrogen. So that one's a little tricky. That's why you see a little bit of difference there. That seems like it doesn't follow the trend. Another example where you see a similar situation is beryllium and boron. Beryllium is 1s2, 2s2. Boron is 1s2, 2p1, right? So although they're both in the second energy level, right? We would expect boron because beryllium comes before boron, so we would expect this one to be higher, but it's not. Its value is 801 as compared to 899. 2p has a higher energy than 2s. So because it's at a higher energy, it requires less energy to remove. Example 9. So you're given some information in a table here on element X. You're given a first through fifth ionization energy, and you're told to investigate, based on this table, how many valence electrons X has. So how can we tell? Well, what we're looking for, we're trying to identify something that looks different in this table. So notice we have 1,000, about 2,300, 4,600, 6,200, 3,700. Where do we see the biggest change? Where do we see something that looks inconsistent with the rest of the table? That's going to be here. Going from 6,000 to 37,000 is an insanely big change, right? So what we can determine from that is that X must have 4 valence electrons, right? So 1, 2, 3, 4, there's not a huge change in energy there. But when we try to remove a fifth, right, a fifth valence electron, there's a huge change. So what that tells us is that the fifth electron must be an inner shell electron and not part of the valence shell, because it requires so much energy to remove, because inner shells are closer to the nucleus, right? We know that. We know that force of attraction is greater the closer it is to the nucleus, and therefore it would require more energy to remove. Okay, we are done with ionization energy examples. Let's have a look real quick at electronegativity. So we don't have example problems with this, but we have some relationships I wanted to review with you that you've seen if you've taken chemistry before. So electronegativity is the tendency of an atom to attract electrons in a bond. And the higher the electronegativity value, the greater the attraction for electrons. Okay? So we use these values to determine polarity of a bond. So this will come into play in future units significantly. So we use these values to classify these bonds as either nonpolar covalent, polar covalent, or ionic bonds. So remember, the greater the distance in the electronegativity values of the two atoms, we say that the more polar the bond is, right? And the greater the attraction for electrons. So if you're given theoretical element X and theoretical element Y that form a bond between each other represented by a dash, right, a single dash line between them, you would always draw something called a dipole, which is an arrow with it looks like a T through the end. It's there to indicate actually a plus sign. You're going to draw that towards the element that is more electronegative. So I'm assuming here that Y is your more electronegative element because my dipole is pointing towards it. What that means, right, when we have a dipole is a separation of charge. And that means that our elements are not equally sharing electrons in this covalent bond. So somebody is essentially hogging the electrons towards itself, right? Because it does a better job of attracting electrons in a bond. So that means that Y is going to be partially negative, not fully, because it doesn't form an ion. It's not an ionic bond, but it is what we call partially negative. Hence, you see this symbol right here, which represents a partial negative. Same thing is represented by a dipole pointed in the direction of that element. The positive end, I like to say, of the dipole represents a partially positive charge, as does an S plus here. Not truly an S, it's a Greek symbol, but roll with me. Okay. The measure, just for your reference, of the magnitude, right, of the dipole is what we call a dipole moment. That's their definition. It's the measure of the magnitude of the dipole. The greater the electronegativity difference, the greater the dipole moment. Now, I did forget to mention that I know that this bond right here, because they're not equally sharing electrons, is a polar covalent bond. There's an unequal distribution of charge. One end is partially positive, one is partially negative. That's a polar covalent bond. This topic is electron affinity. Okay, so this one's a little tricky. electron affinity is the most specific out of our other trends, and it's also the least consistent in trend across the periodic table. So what you need to know is that generally the greater the attraction between an atom and an added electron, the more negative the energy change value will be. So I want to remind you, electron affinity is about the energy change that occurs. Okay, and also this one deals with elements in a gas state. This one's really specific, right? Gas state only. And none of the other trends reference what state of matter the element's in. Now, this one's less predictable, like I said, than other trends, because it just doesn't follow quite as well. So delta E represents an energy change. Okay, delta means change, capital E represents energy, or an E with an exclamation point. You'll see that often. So when delta E is negative, that means the energy is being released. When delta E is positive, that means the energy is being absorbed. So our last example here is example 10. And you're given an equation where you have a neutral gaseous fluorine atom, and you're showing that an electron, E negative, is being added to it. And when we add an electron to it, it forms the ion F negative 1, right, again in the gas state. And we're given a delta E in energy change, which is a hint for us where we may be looking at electron affinity. This value in addition to the gas state, right, of negative 328 kilojoules per mole. So what you need to know is that generally more energy is going to be released when a non-metal gains an electron than when a metal gains an electron. Okay? And electron affinity tends to be positive for the noble gases. So a few little pieces of information to know. This is not as big of a topic, I would say, on your AP exam as, say, ionization energy or radius is, but still important. So this is an example of something you might see referencing electron affinity, and this concludes topic 1.7.